Hello, everyone. Good morning, good afternoon, and good evening, wherever you're joining us from. My name is Ravi Sivalingam from Qualcomm AI Research, and welcome to the next installment of TinyML Talks. Today, we have David Schwarz from Edge Impulse here to talk about TinyML, AutoML plus TinyML with Edge Impulse's EON Tuner. We'd like to thank all our TinyML Talk sponsors and strategic partners, EON Devices, ARM, DeepLight, Edge Impulse, EMSA Visual Sense, Greenwaves Technologies, Gravity Inc., Latent AI, HOTG, ImageMob, Maxim Integrated, Keekso, Reality AI, Seed Studio, Sensimal, SynSense, and Sentient. Additional sponsorships are available. Please contact Olga at tinyml.org. I'd just like to remind everyone that the TinyML Asia Summit will be live online on the first week of November. Please go to the link here to register or use the QR code. We'd like to thank all our sponsors for making this event possible and the technical program committee for all their hard work. I'd also like to mention that the TinyML Vision Challenge conducted by the TinyML Foundation in collaboration with Hackster, it just concluded last week and the winners were announced. Please go check out the results on Hackster or on the TinyML website. A reminder of our next upcoming TinyML talk on Thursday, October 14th by Jan Yongbom, co-founder and CTO of Edge Impulse. He's going to talk about chasing cows, making Africa smarter with embedded ML. Same time, 8 a.m. Pacific. And if you're interested in giving a talk, please contact talks@tinyml.org. All right, David Schwarz is a user success engineer at Edge Impulse, helping customers build and deploy products powered by machine learning. He's a University of Texas graduate with previous experience in embedded systems design and applications engineering. He lives in Austin, Texas, and enjoys reading, swimming, and programming in his spare time. Take it away, David.
Thanks so much for the introduction. And hello, everyone. Thank you for joining this talk. I'm really excited to be here. And I've got a lot of cool work that we've been working on lately at Edge Impulse that I'm very excited to share with everyone. So today, my goal is to provide an overview of our new AutoML tool, the EON Tuner. I'll be discussing kind of what AutoML is, why it's useful, especially on embedded systems, and how our implementation with the EON Tuner works and how you can use it. So let me first give a bit of background on kind of what we do at Edge Impulse, kind of why we're here. So if you're not familiar, we are an embedded ML platform, and we provide the kind of software and framework to kind of collect data from live sensors in the field, work with that data to develop new and novel TinyML algorithms, and then evaluate, test, and iterate on those algorithms to find useful and new techniques for discerning higher level features from that sensor data. And then we also help rapidly deploy those trained models back to the device. So we are a very developer-focused platform, and we really want to give that capability, that ability to do all the things I mentioned before, and put it in the hands of any product designer or team. You don't need to be a data scientist to use our tools. And in fact, many of our developers, who we have over 50,000 now, are from all different industries, all different areas of expertise. And we have a lot of, we provide a lot of tools and novel features that make it easier and I guess as seamless as possible to develop your TinyML applications. And our EON Tuner, which I'll be talking about in depth today, is one of those tools that we've recently released. So to start, or to go from here, I want to give a bit of kind of an overview of what it looks like today to develop a TinyML application. So what we're really looking to do with TinyML is we're going to take a bunch of input data, either from live sensors in the field, maybe a pre-collected data set, or something like that. And we're going to train a neural network on that input data in order to accurately extract some sort of higher level feature that we're looking at. Maybe we want to detect a certain event, like someone saying a keyword. Maybe we want to detect the presence of a person in an image. And we then will deploy that trained model onto the device, optimize it to run as fast as possible with the limited resources available on that sensor or that IoT product. And from that, we get a lot of advantages. When you run these embedded algorithms on a device, you're compressing all of the information that you gain from your data sources down into a much smaller and much faster to compute format that the device can run locally. It doesn't need to be connected to the internet to gain context about its environment and, like I mentioned before, detect those higher level features. So this is a really powerful tool. And when you're comparing kind of how this sizes up based on your older kind of traditional model for developing sensor devices, developing IoT products, the previous kind of paradigm is rule-based engineering, where domain experts, very knowledgeable about maybe the system, the data that they're working on, very skilled at creating good DSP algorithms or things like that, would hand design or hand tune the algorithms required to process data and extract the features that you're looking for. Alternatively, if you can't do that, you might put a human in the loop. You might stream your data to an expert who will manually analyze what's going on. You can think of this for prior to kind of TinyML and image classification being a feasible task. You would need a person to hand analyze what's going on in on a camera or something like that. And so there are lots of situations where this process doesn't scale. For systems where you have to put a human in the loop, that's a lot of overhead. And even before that, if you're hand designing algorithms for every use case, that limits the speed at which you can develop new algorithms. If you look at things like in biometrics, like calculating heart rate, those algorithms, calculating heart rate from, say, an IR sensor, those algorithms were very precisely tuned over decades and decades of research, but that might not extend to a novel problem with a new sensor, a new type of data. And so what TinyML enables and what we really try to allow engineers to do with Edge Impulse is move to this data-driven engineering loop, where we kind of turn that process, that traditional process on its head. And you start with collecting real data that you're going to be seeing in an environment. You then explore the space of algorithms and processing techniques for extracting the features that you're looking for from that data. And then you iteratively repeat that process, adding more data, adding new features that you want to detect, and testing new algorithms in a rapid kind of programmatic way to be able to arrive at a high performing result. And this has huge benefits when you're scaling up to a ton of sensor data that maybe, again, a human might not be able to process, or new feature types that you don't know how to handle from a DSP perspective or a manual hand-tuned algorithm perspective. But when you do this loop, there's an interesting dynamic that happens in this design phase shown on the right, and that design phase is that in an ideal world, we would be able to just take the data and, without knowing anything about the feature extraction process, just get some good results and be able to validate them and iteratively run through this loop with no expertise required. However, unfortunately, in reality, that's not the case, and there's a few reasons for that. So the first is, if you look at this pipeline shown here, this is the traditional flow that's used for a lot of, as I mentioned before, a potential use case, detecting that a keyword is being spoken. So in this case, it's specifically looking for someone in the vicinity saying the word yes, and classifying that differently from other spoken words. And there's been a lot of research around how to effectively do this and how to effectively do this on very small devices. And the one of the most common approaches around this is shown here, where you compute a spectrogram or a spectral-based image that encodes the information shown in that kind of time series audio waveform on the left. And then you run an image a small image classification neural network on that spectrogram in order to determine what type of word is being spoken. And this is commonly used for a lot of kind of voice applications, a lot of audio applications, this general flow. But when you look at this, and as we'll see in a little bit when I'll go through the live demo, there are a lot of hand parameters that you need to tune in this loop. How high of a resolution of a spectrogram do I need? How big of a neural network do I need? What neural network architecture should I use? These are all questions that you can't, you won't always know or won't be able to immediately know what the optimal answer is. And so you might have to try a bunch of different ones and do that kind of iterative process. But if you have to do that manually, or if you have to change your code or your framework for each new type of, each DSP parameter or each neural network architecture, this can be a pretty slow and painful process, right? And furthermore, on embedded systems, this becomes even more tricky, because you can't just say, oh, how high of a resolution spectrogram do I need? What neural network architecture is the best at classifying this audio data? You're working in a very constrained environment, and those decisions have large performance impacts. Raising to a really high resolution spectrogram might not fit in the memory of the device. So that's not an option. And those constraints can be even trickier to work with, as I mentioned kind of earlier when talking about the flow, you're training all of this in a kind of host system, an environment where you have access to all this data, all this compute resources, but then you're deploying it down to this very compute constrained device. So our kind of, one of our primary goals at Edge Impulse is to kind of solve all these problems that I've kind of brought up. And a really cool tool that we've developed around this is our EON Tuner. And I'll be giving an in-depth demo of how this works, how you can use it in just a couple of slides. But we've recently released this tool with the high-level goal of automating that process of iteratively searching for different signal processing, pre-processing techniques, different neural network architectures, and determining what fits the best for your specific application, for your specific environmental constraints. This is public now. Anyone with an Edge Impulse account can create a project and use this tool, or use this tool with an existing project. And we also have some expanded features around working with this through an API for maybe further automating it, completely script-based EON tuning being released later this year. And so again, one of our main focuses when designing this was not to just determine what the kind of best or the ideal algorithm is, or DSP is for working with a certain signal, but to really enable hardware that previously would be very difficult to work with for machine learning, or just exists in the field now and isn't very intelligent. If you're looking at older generation IoT devices where maybe all they do now is collect data and stream that data to over a wireless connection to some server for analysis later on. those devices might have a little bit of extra compute, a few extra compute cycles, a bit of extra RAM on device, a bit of extra space in flash. And if we can update those devices, if we can work within those constraints of limited RAM, compute, and memory, we can add intelligence to them without having to upgrade any of the hardware. We can do that fully in software. And that's really valuable just from a lot of perspectives, from increasing the longevity of devices, from reducing waste, and from working with in situations where you might not be able to get the latest and greatest silicon for a given application. So with that, I want to hop into a live demo. I think this will be a much more interesting kind of look at how this works, what it can really be used for, and what the kind of capabilities are. So what I have here is I have a demo project that we've created at Edge Impulse. And the idea is that we're trying to differentiate between two different species of bird calls. And this is kind of analogous to a lot of other audio-based applications where you might want to detect human speech. You might want to detect kind of a continuous sound like a faucet leaking, or you might want to detect a discrete event like a glass breaking or something like that. And so the project that we're going to show here is one where we've already a while back designed an algorithm to process this audio data, which as you can see here, let me just show it, is just the sounds of different bird calls collected over kind of 8-second, kind of longer windows. And if we look through, if I filter this data, you can kind of maybe get an intuitive difference of maybe how these bird calls might differ from one species to another. But as you can see, this is a pretty complicated signal, right? There isn't an immediately obvious, at least, just looking at it, glancing at it, what the different species correspond to. So, we designed an initial algorithm that can process this. And to do this, we used kind of the Edge Impulse UI and Edge Impulse Flow to do so. So what you're looking at here is the impulse, which is what we call kind of the holistic design of that DSP preprocessing plus the neural network. But the flow to go from, I have a 2-second window of raw audio data, and then the kind of 3 specific features of, is this a house sparrow? Is this some other sound? Or is this the parakeet? And if you look at this, what we did originally is we're running an MFCC preprocessing block. And so MFCC, it's commonly used for human voice, but it can also be good for, as we found, non-human voices in terms of extracting frequency domain features from the time series signal, and then generating that 2D spectrogram image that you saw in the slides. And we'll see that in a little bit. But also for different applications, Edge Impulse offers a lot of different common DSP preprocessing layers that we found to be very effective across a variety of applications. For more than just audio, right? You can work with any time series sensor, and we have preprocessing and support for images, object detection, things like that as well. And so all of this is enabled through a relatively small number of kind of common DSP blocks that we found to be effective across many different situations. And just to note, if you are working on some interesting use case and you're a DSP expert, and something that works better than MFCC or something like that, we fully support kind of custom blocks too. So you can go in, host your own kind of DSP preprocessing code and just work with it within our studio. And then after we've done that MFCC block, we're then just running a TinyML neural network classifier to kind of go from that 2D image spectrogram to our classification. So let's save this, and let's take a look at our MFCC really quickly. So here you can see kind of what this generated 2D image looks like. You can kind of see how it encodes the data, and you can kind of see how it potentially changes as the window slides along the sound of this parakeet calling. If you look here, though, and this is where we start to get into the use case and the interesting applications for the EON Tuner, there are a lot of parameters here that could be that can be changed. For instance, I can double my FFT length. I can change the number of Kepstro coefficients, or I can even just change the frequencies that are filtered out before we even generate this image. And it's difficult to know, especially if say I'm unfamiliar with this MFCC technique, or if I'm unfamiliar with the exact nuances of the data that I'm working with. It can be very difficult to know what a good parameter set here is. And the decisions made here will have a big impact on what information is even available for the neural network to classify later on. And so I'll kind of get to the solution and how the EON Tuner addresses this in a little bit, but that just hopefully gives an overview of, you see kind of this list of 10 parameters, and the kind of first problem we run into is, what values do I select for all of these? And so my solution for this so far is just to go with the defaults. I've just kind of, at Edge Impulse, our platform suggests kind of sensible defaults that we think would maybe be a good fit, a good starting point for your application, but we don't necessarily know that ahead of time. So here we're starting out with just only using these default parameters, which might not be the best, right? And going through the flow, when you work with our platform, basically the way it works is you'll select your DSP parameters, and then you'll go and you'll generate that spectrogram for every single slice of data in that data set that we collected. And so from here, you'll get a cool visualization of like how similar different classes of data are from one another. And you can kind of see there's kind of a layered relationship between the different classes here, which is potentially interesting. And then also important to note here is the processing time and RAM usage estimate. So computing that spectrogram on device can be an expensive process, especially depending on what device you're using. Here, we're just showing the estimates for a generic Cortex-M7 device. But 26 KB of RAM might be a significant amount of overhead, depending on the exact system that you're working in. And so this is another area where if we get to the end of this process, we generate our features and this just won't fit on the device, we kind of have to go back to the drawing board potentially. And so the EON Tuner is going to help us address that as well, as we'll see. And then now that we've got our deep DSP pre-processing, we're going to kind of work in developing a neural network. And here again, we have a lot of different options to select from, and it's not clear what kind of the optimal solution will be. As you see here, before we get to kind of what's up here, for the network architecture, we suggest some sensible defaults, which you can see here, but we don't know necessarily that what kind of the ideal scenario or the ideal model architecture is for an exact given application. And if you're not a data scientist, if you're maybe not super familiar with what different types of neural network architectures or different layers mean, this might be very confusing. It might be difficult to determine even where to start from. Should I use a 2D convolutional layer or a 1D layer? Does that make sense for this application? These are perfectly valid questions, and ones that you, without the EON Tuner, would have to kind of manually experiment and iterate through. And if we're looking kind of up here, we also have additional questions around how long should we train for? What should our learning rate be? Things like that. And so these are also parameters where it's not immediately clear what the optimal solution is. And so I've already gone through this training process for a first run, just to not take up time watching it kind of train up. But the end result is we have pretty good accuracy. We're at about 90%. And you can see down here, here's kind of the estimate of what it's going to take in order to actually run the neural network. And it's important to note that this is in addition to the cost of generating that this MFCC spectrogram. So there's a cost associated with the DSP in terms of compute and memory, and as well for the neural network. So now I get to the cool part, and here I will just kind of show the EON Tuner, and I'll give a description of what it's doing, and then I'll kind of give a description of kind of hopefully what this AutoML process looks like. So AutoML as a concept, the general idea that we're going for here is we want to, from a given relatively sensible starting point, get some parameters, maybe some defaults suggested by the Edge Impulse Studio, for instance. We want to randomly, we want to search through the space of possible model architectures, DSP parameters, and compute constraints, the RAM, flash usage, and latency of those different model architectures and pre-processing models in order to arrive at a solution, one iteration of the model that fits our application as best that we can. So in this case, we're really looking for a model that will fit on the device in the RAM and ROM that's available. And we want it to run in real time. So we want, if we look at our impulse over here, we're potentially wanting to run every 500 milliseconds. We would want to slide our window over and test a new sample. And so in the tuner, we want to look for samples that are kind of under that time threshold. And we're going to search through that space, and we're going to run training. We're going to run this feature generation and slicing up of our data set and training process for each different configuration. And then we're going to compare how they perform against one another. And so the way this works in our platform is you kind of get to this tab once you've kind of trained an initial model. And then you select some constraints around what type of target you're looking for. So here I'm running, I say, okay, I want to be detecting kind of something analogous to keywords, like it's kind of a bird call. And I want to be working with this Cortex M7 based device. And then I want to set my inference time. I'll do this in a little bit just so I don't force a restart of the training. But I want to set this for whatever my time per inference limit is, whatever amount of compute time I have available on device. So you can think of this in a lot of different perspectives. So if you're looking at this from a sensor perspective, you want to be able to run your neural network if needed in real time. And so you wouldn't want this to be larger than, say, the window or the window sliding interval that you're running inference on. Other constraints might come around other high priority processes that need to run on device. Like say you're maintaining a wireless connection over Bluetooth or something like that. You might not be in a situation where you don't want to wait, 10 milliseconds or whatever that is for that interval. And you don't want that to happen right in the middle of an inference. So you might want to set that to a smaller number than 10 milliseconds or whatever that external constraint is. But the idea is that from here, you can select between the different devices with different memory and compute and kind of core frequency capabilities. And this time for inference, you can kind of get an idea of the constraints of your device, your application. So then from here, you just hit start the EON Tuner, and it sometimes can take a couple hours to run because again, you're training all sorts of different models and model architectures. But at the end, you get this comparison shown here, where we can see all of the different model architectures that our tuner tried, and we can see how they stack up against each other. So I can look here at the this second model, and I can see, okay, what did it try and do here? So it tried out a model architecture with a bunch of convolutional layers, and it tried out an MFE block, a different signal preprocessing block to kind of test performance ahead of time, to pre-process the data. And maybe that has some performance advantages over the MFCC block. And so when we have these, what we're seeing here is the kind of default scoring of these models. There's a bunch of these options that we can scroll through, but we're probably only interested in the highest performing ones. And so we can sort the models that we've tested against different metrics that we care about. So as I mentioned earlier around latency, maybe we need to run this model very quickly. And we want to see what the fastest performing, lowest latency model architecture was. That's still relatively accurate, relatively effective for what we're looking for. So if we do this, we can see there's a few different options. This one looks to be performing pretty well with 107 milliseconds of overhead. And so that's an optional constraint that you can base different model designs against. Say again, you're working with an existing device that has a few milliseconds of spare cycles. You can constrain a given model for that, and try and see, okay, can I get a model design that will fit on that device? And we can do the same for memory too. We can look for models that take the smallest amount of memory possible, and we can also change this to show us what our test accuracy looks like. Maybe we're more interested in, and in a lot of cases, you're much more interested in looking at data that maybe the network's never seen before during training, or a real life example that might have more noise, more environmental factors going on that you add in kind of a test data set. And we can test against this here as well. And so here you can see kind of a few different options for decently performing models with this framework. And so what's really cool about the tuner, and there are a few features that I want to point out here, is that if you look at what AutoML traditionally does, a lot of frameworks out there, such as Keras, which we're using for the model portion of this, or TensorFlow, or other frameworks, support some kind of AutoML tool. But usually that's limited to just the neural network architecture itself. But the neural network architecture is only one small part of this equation. In fact, as you can see here, the input window, like how big of a buffer do you send into your input data, or what type of pre-processing you perform, and what type of parameters you use around that pre-processing layer matter a lot. And as you can see here, there are some kind of maybe key selections that the higher performing models are suggesting are effective. And so by kind of maintaining that whole pipeline and treating that whole process of collecting data and processing as a holistic thing, we're able to easily iterate on and explore the space for the DSP, the input, and the neural network, which is a very kind of novel feature, and it's very cool and it's very powerful. And so once we have a model we've selected against, say here we're just interested in accuracy. As you can see here, we have plenty of memory on these devices, and we want to see, okay, I want something that's very good at test accuracy, and maybe even more defined. We want to see we want to be specifically accurate at detecting, accurately detecting between the case of, oh, there's noise present and there's some species of bird. Maybe we can tolerate a little bit of reduced accuracy for what type of bird, as long as we're picking up that it's a bird that is speaking and not some other sound. And so we can calibrate, as shown here, on the highest performing model just for accurately detecting noise. And so that's what I'll work with, just to kind of show the example. And if we see here, we can then select this and we can update our model. And then from here, we'll be able to see our new, once it loads, our new pipeline. And so if you're looking here, these are all tuner selected parameters. You see this new generated spectrogram that looks very different from our original. And in our neural network, you'll see the novel neural network architecture. And so what's cool is that once you've gone through this tuner, you still have full control to edit, to kind of iterate on this yourself manually if you want to do that manual exploration. Like the tuner isn't the end all be all, but it's a fantastic starting point to go from, okay, I have no idea what to do, so I'm just working with the defaults, to I have something that I know is in the direction of a very effective or close to ideal model. And so from here, we can then run this through the same existing kind of edge impulse workflow around testing performance. Here we can see how the kind of, that just like we saw in the tuner itself, we can see that it's very accurate. It's beating the accuracy of our original model on noise. And then it's around equal on detecting the presence of what specific bird call is occurring. And we can also then work with the Edge Impulses versioning tool to create a new version that just says, okay, this was our EON Tuner initial run. And from here, we can kind of store this version and save it. And then if we're experimenting with lots of different types of tuner architectures and models throughout, we can save a snapshot of that model. And actually, let me cancel this really quick so I can show another part. We even support a more granular version of this, where you can save and store a specific version of just the DSP or just the neural network, just by this kind of versioning tool on the left. And this lets you get a finer grain control than the kind of project level versioning shown here. But the idea is we want all of this to be reproducible. We want you to be able to iterate on your models and develop new insights from your data, and then take a snapshot of that. Know, okay, I've locked in, 95% test performance on detecting noise, and then kind of iterate from there further and see if you can do any better. And so with that, I think that kind of mostly covers through what I wanted to show in terms of the demo today. This EON Tuner is available for all Edge Impulse projects. It's completely free for users to take advantage of. And it works and can apply to existing projects as well as new ones. And it'll work across all different types of data. The example I've shown today is audio, but we've also recently enabled this for accelerometer and image-based projects, which is really cool. And so I'll hop back into the slides, but hopefully from this, you have an idea of how you can use the EON Tuner in an Edge Impulse project. And hopefully you also have an idea of what AutoML is kind of here to solve, and why this might be useful for some of your projects. So with that, I'd like to hop now into answering some questions from the audience. If there's anything we don't get to over the course of this, feel free to email me directly at david@edgeimpulse.com. I'm always happy to answer questions and discuss cool topics or interesting queries on machine learning. And yeah, with that, I think let's go to answering some Q&A questions.
Thank you very much, David. That was really great. I really enjoyed the live demo walkthrough. That's always fun, seeing things in action. We have a bunch of questions, and while I'm asking the questions, audience members, you'll see a poll pop up. Please do answer that. That helps us deliver and improve great content to you all the time. Yeah, so some of the questions are, for example, Marcelo is asking about whether the EON Tuner is available only for audio, or does it cover accelerometer or video data as well?
Yeah, and so as mentioned, we recently released this. It was originally released only for audio, but we recently published it for all data types within our platform. So that means any time series sensor, so accelerometers, temperature sensors, current sensing, any of that, audio, as well as images and image classification and even object detection. So yeah, it works for everything.
Thank you. And by the way, just a reminder to the audience, please ask your questions in the Q&A window. There's some other questions, and these may not be particularly related to Tuner per se, but I think this would be good to ask. In these audio examples, do the sound files need to be of the same time length?
Right, so they don't actually. And so the way this works is that in Edge Impulse, when you saw on the Impulse Design tab, that first option was around selecting the window size. And say you have, an 8-second long sample of data, and we've selected, a 1-second window that we're going to run inference on. So what our platform does is it slices up that sample into 1-second increments. If there's, you can configure how to handle that last. If there's kind of an overhang, you can configure to either zero pad it or discard kind of extra data at the end that doesn't fit fully within a window. But you basically will just slice those longer samples up into those smaller windows that'll then be fed into the network. And the idea is that you want to configure your window size based around the features that you're trying to detect. So if I'm checking for a word that takes someone between 1 and 3 seconds to speak, I want to be able to capture that full 3-second window. Then you want to have samples that are around or longer than that period. They don't need to be the exact same time length, and we kind of operate on that kind of windowing implementation.
Got it. Thank you. Another question is regarding noise. So in your particular example that you showed, noise was one of the classes that you trained, sort of like a background class, right? So somebody's asked whether you can use noise cancellation as a pre-processing step if you explicitly provide it, or I guess my question on top of that is, do you need to if the neural network can be trained to be robust to that?
So that's definitely interesting. There's a few different approaches. As you mentioned, the approach we're taking here is we actually train the network to kind of detect noise. A lot of the samples provided here for noise are kind of close to white noise or just kind of generic background noise, right? Where you can train a neural network to detect, I'm just seeing kind of noise across a large portion of my frequency buckets or whatever your pre-processing kind of converts that to, and train it to detect that and differentiate it from your network. Now, the other approach that you can take is you can train your network to be noise resilient by training it to, rather than detecting noise as a discrete class, say I'm not in an environment where just noise will occur. There's always going to be something else that I'm trying to detect. If you train the neural network on samples in the presence of noise, it can become robust to that, as long as that noise is representative of what will be there in the real world when this is running for real. And then the third and final way this can be approached is, since you have full control over that pre-processing, you can filter out noise that you don't want, right? I could set my MFCC layers to just exclude high or low frequency noise, for instance, in a simple case. And so you could pull out noise manually that way. But ideally, kind of in the spirit of that data-driven approach, it's more ideal and a little bit faster moving if you can bake that into the neural network or the DSP kind of search process.
Got it. Makes sense. Another question about, is there any kind of reference publication or documentation that explains a little bit more in detail about what all the different blocks do and what the parameters in each block does?
Yeah, so all of this, all documentation on each of our different DSP and neural network blocks can be found at our website. I will pull that up. I'll pull that up real quick just to show.
Sure.
If you just go to docs.edgeimpulse.com, if you go here, we have a full reference for all of our APIs, all of our neural network blocks, everything in around there. So this is the place you should go if you're interested in kind of getting the details on what everything does.
Great. Oh, by the way, since you brought that up, I had a question, and I think there's somebody else who asked a similar question, so you have all those dev boards listed in your documentation page. In the tuner, I think your hardware selection choices are kind of a little more general, right? Like they're like Cortex M7 or some other Cortex M3 or M4F. Do you, can you tune across, first of all, across different core architectures? For example, you can say for this problem, I only need an M4, not an M7 or something like that. Or do you only allow selecting one particular core and tuning for that?
Yeah, so the way I would approach that is right now you do have to manually run the tuner for a specific core, and that's really just because of the way the how we're kind of estimating performance. It's kind of baked into that one EON Tuner run. But in theory, you definitely could do this automatically. But the way it works right now is if I think you even saw this on given I just arbitrarily selected 100 milliseconds, right? And the fastest performing model was around 106, 107. So, in that case, we weren't able to find something that was working within that bounds. And if that's what you run into, the tuner will show you, oh, you're over, we can't get to real-time performance on this model. And so then that's when it might be time to kind of bump up from that, Cortex M4 to the next class of processor. So you definitely can do it. There's just a little bit of kind of manual looking to be done right now.
Got it. How about compare tuning also in a similar way, not in a general core name, but also across the dev boards that you have support for? I don't know if that's something that you do or planning to do. I realize there might be some concerns about recommending one board versus another. So.
Oh yeah, no, definitely. So we work with many different vendors for all sorts of different kind of classes of targets. At a very generic level, we're working with everything from a Cortex M0 Plus all the way up to like an NVIDIA Jetson Nano or Raspberry Pi. So like high tier ARM processors with or without kind of a GPU analog available, right? And then in between that, there's everything. We work with accelerated DSPs. Like I think you might have seen in the list, there's one ARC DSP based implementation that we have kind of data for that's very fast and kind of power per performance much better than what you get for specific neural networks than a generic processor. And then we're also working with a lot of, there's a lot of, on the silicon side, a lot of development around, neural network accelerators, doing that in hardware. And so we're working with a bunch of different vendors on accelerators, and they all have their different kind of flavors and different kind of optimizations that they're aiming for. So yeah, we try and work across a variety of everything so that we can kind of give a view of what those trade-offs look like. Yeah.
Got it. A related question is, can the shape of the input and the kernels be tuned for performance cycles for a chosen target? For example, shapes that fill up like SIMD lanes or avoid unaligned access of memory access.
Yeah, so right now, a lot of that is kind of baked into a lot of the base assumptions we make around our DSP. So like on like the SIMD side, I don't know if we've directly done anything around optimizing for that or utilizing that. Mainly as on a lot of the cores we support, that sort of feature just isn't available, on smaller Cortex M devices. But in general, for a given device, we will try and implement very optimized and as fast as we can possibly get them kernels for both running the neural network layers and running the DSP. And when we do that, those performance considerations come into play. So I think if you look at like a good example of this, what I'm thinking of is if you look at like the FFT links that we support, it has to be factor of 2. Like you're not going to be able to run some arbitrary FFT link, or you might be able to, we don't recommend it because it'll be slower. So like we have some recommendations around there around kind of getting those low-level performance optimizations, but I would say in most cases that happens a little bit before the tuner comes into play.
Yeah, there are a bunch of other questions. Let me dive into a few at a time. Is it possible to evaluate short video clips for vision problems? like for sign language translation?
So not today, but that's something we are working on, and we have a lot of really cool features coming in the very near future around this. So we have two features. So first, we are working on like proper video support as a file format, and then we additionally are we announced this a couple weeks ago, but we're also working on some novel machine learning algorithms that allow you to run real-time object detection on embedded devices. So right now we support object detection on a Raspberry Pi and up, kind of in terms of computational complexity. But with this new technique that we're hoping to release, I believe early next year, you'll be able to run this on Cortex-M devices. And so with that, you might be able to run images at a high enough frequency on, say, a Raspberry Pi to do kind of real-time image classification or real-time object detection enough to suit whatever video needs you're looking at. Or hopefully eventually we'll be able to give that kind of first-party video support.
Excellent. And another question is, does Edge Impulse work on color images, which I think you do, but second part of the question is images of arbitrary size. And I think what the person is trying to ask is, there are these fully convolutional networks that can run on, you don't have to specify that it's just 224 by 224, right? So it can run on images of arbitrary size and provide proportional outputs. So is that something that is currently supported on Edge Impulse?
So right now, no. Our image classification and object detection utilize like a mobile v2 based approach, which does constrain the input size, mainly because we're working from like a transfer learning model to kind of, not to go into too many technical details, but it's a transfer learning based approach where we kind of have pre-selected a few common resolutions. However, that constrained object detection I mentioned, running object detection on M4s does utilize that kind of fully convolutional technique. And so that's something where we're hoping that potentially we can support an arbitrary image size once that's released. So definitely keep an eye out for that if you're looking to work with like very large images or arbitrary image sizes, something like that.
Got it. Another question is, if I have my own data set, could I keep it local and use my own GPUs, or do I need to upload it all onto the Edge Impulse servers and use the Edge Impulse compute?
Yeah, so our platform is cloud-based, so you'll need to upload your samples to kind of use our platform tools. We do try to offer a lot of flexibility around like exporting the trained model, both in terms of the Python code that's generated for the DSP layers and neural network architecture. So you can grab that Python code and you could potentially kind of roll your own. But yeah, most of our workflow is kind of based around uploading your data and then working through our cloud platform. Yeah. Got it.
And along those lines, some deep questions about, does Edge Impulse offer a free evaluation account? Is it 60 days?
Yeah, so our platform is completely free. So you can create an account at edgeimpulse.com and it'll be free indefinitely. We do have some kind of compute resource limits around free accounts, but most of our tools and workflows are kind of designed to fit within that. So especially if you're in kind of that prototyping stage, the kind of free compute that you get from us is more than enough. And so yeah, it's for most practical purposes, it's completely free to use.
Got it. Another question is, does the EON Tuner scale up to larger image classification models and data sets, or is it too expensive to train and tune and practice?
So in theory, you can. Right now, a lot of our image classification demos and models, we use that kind of transfer learning based approach I mentioned earlier. But if you have a huge data set, if you have enough data to fully train MobileNet V2 from scratch, for instance, you can do it in our platform. I didn't really show it, but we give access to kind of the backing Keras code that you can edit directly. So you can import any model architecture supported by Keras and TensorFlow Lite for microcontrollers, and you can train it from scratch. And you can use the tuner with that. So you definitely could, in theory, select an arbitrary image size, train your model from scratch and go from there. I just caution that you might need a lot of data, and that might be a little bit beyond kind of the compute limits that a developer account would have initially. But for things like that, definitely reach out to me, and we're always happy to work with people who are doing interesting and novel use cases on our platform. So yeah.
Excellent. Is the EON Tuner available for download or only used in the cloud? I guess that goes to your previous answer.
Yeah, so this is the same kind of thing where the tuner capability is really tied to our kind of cloud compute platform. So you'll need to work within our web-based studio in order to kind of use it.
Got it. Do you support NN architectures like Conval STMs?
So right now we don't support LSTM or kind of our RNNs in general. We found in a lot of cases that for that specifically, not to go off on a total tangent, they're a little bit expensive for the value that you get on these kind of constrained environments. But at the same time, we're always working on developing new layers. And what I'll add is, again, I mentioned you can kind of go into that Git access and write direct Keras code. And so you can if something's supported in Keras and a TensorFlow-like for microcontrollers kernel becomes available, you can implement that model, and then you might need to do a little bit of manual code to get that running on device, but it's possible, and we provide the source code for everything that our platform generates in terms of the C and C++ sources that would run on device. So in theory, I think things like RNNs, as support gets added in TensorFlow-like for microcontrollers, it's possible to start adding that, maybe even if we haven't implemented that quite yet ourselves, or haven't found the need to do that on our platform quite yet. Yeah.
That's good. All right, a couple of last questions, and the remaining questions will continue in the TinyML forum. Do we have to pick and specify a particular edge device when starting a new Edge Impulse project? Because even before you run the tuner, you see inference time and memory usage particular to a device.
Yeah, so it will default to, if you don't give it any information about what device you're working with, it'll just default to, I believe, a Cortex M7 that I showed, or we offer a few generic devices. So it'll provide you a default. But in that dashboard view, that first view that I showed, you can select and change devices there as well. And that selection from that main dashboard page is what drives those initial estimates on RAM usage and for RAM usage and compute. And then the EON Tuner view just lets you kind of change that if you realize, like, as you mentioned before, I might need a bigger, higher performance device to be able to run this sort of model that I'm looking at. So yeah, it's available on that dashboard page.
Excellent. All right, and just to kind of wrap up, I'd like to add one of the things I really like about EON Tuner, in addition to all the great features that you talked about, and I've tried it out, and you can just like close the browser and come back later and it's still available, right? So especially if it takes a little bit longer, I don't have to worry about if my computer reboots for some reason, I don't have to worry about losing all that progress. And that's really great because of it's hosted on your servers.
Yeah, exactly. Yeah.
Excellent. Well, that's all the time we have for questions right now. There are a couple of more questions. We'll post them on the TinyML forums. So I encourage the audience members to go to tinyml.org/forums or forums.tinyml.org and check it out. And David and the rest of the Edge Impulse team can answer them asynchronously. Thank you so much, David. This is a very interesting talk, very enlightening, and great to see a live demo. And thank you for answering all these questions that came up.
Yeah, thanks so much for having me.
Yep. All right, we'd like to thank our TinyML Talk sponsors and strategic partners again. ARM, architecting a smarter world, powering innovation through AI. DeepLight uses AI to make other AI faster, smaller, and more power efficient. Edge Impulse enables developers to create the next generation of intelligent device solutions with embedded machine learning. EMSA Visual Sense, EMSA, the I in IoT, enables edge AI through ultra-low power visual sensors. GreenWaves Technologies, enabling the next generation of sensor and hearable products to process rich data with energy efficiency. HOTG, building the distributed infrastructure to pave the way for AI-enabled edge applications. Latent AI, adaptive AI for the intelligent edge. Maxim Integrated, the new Max 78000 implements AI inferences at low energy levels. Now the edge can see and hear like never before. Kixo AutoML, the automated machine learning platform that builds TinyML solutions for the edge using sensor data. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Reality AI, with pre-built edge AI sensing modules plus tools to build your own. Sensible, pioneering TinyML software tools that auto-generate AI code for the intelligent edge. SynSense builds sensing and inference hardware for ultra-low power embedded mobile and edge devices. And Sentient, moving artificial intelligence and machine learning from the cloud to edge devices. Just a reminder, our next TinyML talk is on Thursday, October 14 by Jan Youngboom, CTO of Edge Impulse, about chasing cows. It's going to be interesting as well. Thank you, everyone, for joining today. And thank you so much, David, once again, for a great talk.